Okay, there are two distinct type of drag forces that we could consider that exists. One for objects moving slowly within a fluid. And by fluid, I mean it's not necessarily a liquid, like, gas, well, like air, you could loosely refer to the, well, I don't want to confuse you. Like, so in some atmosphere or some medium, let's just say medium, we can have an object moving through that medium and with a speed that is high magnitude or a speed that is relatively low magnitude. And what we find is that drag force is proportional to speed. It's proportional to how fast something is moving. Well, in fact, what we say that for slow-moving object, the drag force is proportional to the speed, yes. But for a fast-moving object, the drag force is proportional to the square of the speed. This is just some sort of, it's an empirical formula, meaning that over years, people just observed objects and took data, and the data supported that evidence. So there's no derivation, fundamental derivation related to derivatives. Actually, we could kind of talk about the fact that it's also related, well, yeah, just that. The force itself is proportional to how fast an object is moving. So for a slow-moving object, we'll say that the drag force F sub D is defined as a constant known as the drag coefficient, we'll say K for slow-moving, times the speed of the object. For an object that is fast-moving object, we will say that the drag force is proportional to the square of the speed. So it's going to be the drag coefficient times the square of the speed of the object. Now, we need examples of slow and fast. What does that mean? Well, technically speaking, a slow-moving object would be like a pearl within oil, or pearl in syrup. You can imagine, you can think of a, syrup, S-Y-R-U-P, yeah. Just imagine a pearl in shampoo or syrup or something, like slowly moving down. And for fast, technically speaking, it might be like a skydiver, technically, or an object free falling in a vacuum. Well, if it's in a vacuum, it's not going to have a drag force, but falling in an atmosphere or something like that. Like if I drop this object right now, technically it has a drag force on it. Now, this drag coefficient here, it's not just related to, we're not going to discuss that. We'll talk about how to calculate drag coefficients probably in Physics 39. It's not something we discuss here. Here we just assume that's a constant that's given to us for a particular medium. But what you find is that the drag coefficient is associated with how the cross-sectional area of the object falling, right? Because, and you know that to some degree, because if you take a piece of paper, and you drop that piece of paper, the amount of drag on that object depends on the shape of the paper. Well, that's incorporated not so much in the force, but in the drag coefficient itself. So here, you drop that object, and it floats down, however it does, right? So clearly, the drag is retarding its motion in a particular fashion. But if I crumple the paper up and change the cross-sectional area, and I drop it, right, the motion is very different. So, sure, that's going to be associated with the force, indirectly through the coefficient, but it directly affects the coefficient. So we're not going to talk about how to calculate that coefficient based on changing cross-section area of an object, right? For this section, we will just discuss that. We'll assume it's a constant. And also, we're still dealing with point particles. That's the other thing, is that at this point, we're still assuming that all the objects that we deal with can be replaced by point particles. So we're not considering any effect of the shape of the object, or at least in terms of the way external forces connect with them. So for those reasons right now, we're just assuming that this thing is a number. But it's a different number for an object moving very fast as opposed to very slow, as we've implied by the different formulas for those slow moving versus fast moving objects. Okay. All right, so yeah, and so we want to take the units for these things are also different. You know, force has units of newtons. So for a slow moving object, I should have done that under here, we can see that the units for beta, or sorry, for K, that's what I've called it, is going to be equal to kilograms per meters. I'm sorry, kilograms per second. And you can work that out. So this guy have to have units of kilograms per second, whereas this thing would have to be kilograms per meters. In fact, let's work this one out as an example in terms of the units. You can go back and do the same thing, verify for yourself that this is true. So on the right side, I have newtons, right? So newtons must be equal to, and this thing is, oh, well, actually, let's do this. This formula suggests that beta equals force divided by the square of the velocity, right? So if we work that out, we have newtons over meters squared per second to the fourth, right? Because it's square meters there. That's the same thing as a newton over 1 times the reciprocal, so seconds to the fourth over meters squared. But a newton is a kilogram meter per second. So I have kilogram meter per second times seconds to the fourth over meters squared. Question? Another question? So we have, yeah, so sorry. Newton is a kilogram meter per second squared, right? Yeah, per second squared. Kilogram meter per second squared. So we have meter cancels one, and so 0. So that's and I have 1 here, and meter per second. You know what? Yeah, I did mess up, didn't I? It's velocity is meter. I'm thinking of acceleration. Velocity is meters per second. So this should have been meters squared per second squared, right? Not bad. Meters squared per second squared, because I'm squaring velocity. Velocity is meter per second, so meters squared per second squared. So is that what someone was going to say? Maybe, I don't know. So that's second squared over meter squared. So this is second squared, right? So then second squared cancels here, and I'm left with kilograms, and I had just 1 meter left there. So in the end, we see that the units for beta for a fast moving object, the unit is going to be kilogram kilograms per meter. Now, if you do a similar unit analysis on K, you're going to get kilograms per second. And so that's really interesting that it's kind of like what happens with the coefficient of friction, right? For the same objects, you know, if the thing is not moving, you have a coefficient of static friction, but then once it starts to move, then you have coefficient of kinetic friction. So it just changes, even though it's the same surfaces. Something like that happens similarly when you have objects moving, and you have to maybe work out why. Object is falling, and you know it has the force, the drag force is, and you know, just like friction, drag is going to be opposite the direction of motion, right? So if you're falling down, the drag force is up. And I just illustrated that with the object, right? Once I decreased it, it fell faster, which means that the force in the opposite direction was less once I crumpled it up. But for some reason, that drag force is proportional to the speed. But when the thing is moving very fast, all of a sudden, it's proportional to the square of the speed. So and there's a critical point where that happens. You know, maybe at some critical velocity, you begin to see that. We don't really talk about, you know, the boundary between when that, you know, happens and when it doesn't. And yeah, we won't talk about. It's probably, I have to get into some physics that I haven't discussed, maybe, or maybe give a qualitative justification as to why that is. Right now, we'll just take the result. Okay. Okay. Now, before we so yeah. So that's the definition of drag. Now, I'm not going to work out the solution for this. Both of these are fairly easily worked out. I mean, once you go through it once or twice and you understand what's, you know, the mathematical tools being utilized. You can work them out the same way, the equations of motion for drag. But we're going to focus on just this guy to work out as a solution. And they actually have most books will work it out, skip a lot of details, but they'll have the solutions in your textbook for the equation of motion, the velocity equation and the position equation with respect to time for an object that is experiencing drag and usually focusing on the slow moving drag. So I'm going to do that for you in class. Now, let me now quickly rederive an equation of motion for an object in a vacuum. Basically, derive the equations of motion that we've already been using, that we were using weeks ago. But remember, then I derived those equations using algebra and basic mathematical definitions. It took us some time to do that. Now I'm going to do the same thing, the basic two equations of motion for an accelerated object. And it was from those two equations that we then developed the other two, the velocity squared equation and the average velocity. But let's show how to get directly to those equations without using math or algebra, but directly from Newton's the laws of motion. Again, this is the genius of Isaac Newton, because to realize the connection between force, acceleration, and the equations of motion. Now, let's say that you have a mass falling in a vacuum, like we've been, you know, free falling object, okay? A free falling object. Now, we said that that if I have an object falling, right, I can see that the motion is accelerated motion because I can look at that motion and know that as it falls, its speed is increasing. And I can take some data and look at the data, and I'll realize that as time, for equal increments of time, the object falls in a larger distance, which means that its average speed is increasing over those equal increments. So that's accelerated motion, that the velocity is changing per unit time. So I would then know that I would have to apply Newton's second law, right? Not the first law, because clearly there's a net force on the object. Why? Because the motion is changing. The velocity is, the magnitude of the velocity is increasing, even if its direction isn't, its magnitude is. So you apply Newton's second law, right? You have the net force, so free falling object, free fall. The net force on the object is equal to the mass times the acceleration. Okay. Now, I have to be a little bit careful about the sign in this case, because I know that the force on the object, the only force on the object is the force of gravity, right? It's falling. Right, so here, this is my mass, M, and if I were to indicate that, here I have the weight on the object, mg, and I know that, well, in this case, we can prove that the acceleration is equal to g, but it has an acceleration in the y direction, right? In fact, we say that we define it as negative g here. Y equals negative g. But coming back to the equation of motion, again, I identify the force on the object. Well, the force is negative mg. Actually, the magnitude is mg, but if I want to be specific in the way that I've defined g, actually, I guess I would I do a magnitude? Let's see, think about this. I have my notes. Yeah, it's going to be a minus. I have to have that minus. In fact, I guess what we would say is we could call it, it's not really a restoring force, because we use that term for oscillatory motion, simple harmonic motion. But I guess what we can say is that clearly that we define g as negative. So if the direction of the acceleration is negative, and that's giving rise to the force on the object, sure, the magnitude of that force is mg, which we usually write the weight as that. But in terms of free fall motion, we actually have to put in that minus sign to indicate that the direction in which we define that force to be, which is negative and down, and associated with that negative acceleration. So mg is negative. The force on the object is a weight, and it's negative because it's pointing down, and that's equal to ma. Okay. Now, in order to derive an equation of motion, we can employ something called separation of variables. That is, so yeah, I can easily see that my mass goes out. So I have an equation that is an equation of motion, and technically, if I wanted to write an equation of motion, I have to write a differential equation. So I could say, I could write it, taking my definition of velocity, of acceleration. And acceleration with respect to time is defined as the derivative with respect to time of velocity with respect to time. So substitute 3 into 2, and I would have a minus g is equal to dt, dv dt. And now I would, so the differential equation that defines this motion is this thing. Taking the g on the other side, my differential equation would be derivative with respect to time of velocity plus g equals 0. So technically speaking, that gives me a differential equation that I can solve to figure out what is the velocity with respect to time that solves that differential equation. That's essentially what you're doing when you find an equation of motion. All right. What is the v of t? What is the form of that equation? That if I substitute that v of t into this differential equation, it'll give me a solution that satisfies the motion that I'm actually seeing here. So it would describe how that velocity is changing with respect to time, if I could find the functional form of that v of t. That's what an equation of motion is. It's a differential equation. In this case, a first order, linear, homogeneous differential equation. So I'm not going to go over what all those terms mean, so I want to stay on the physics. But if you've had differential equations, this would be one of the easiest differential equation problems that you could solve. Homogeneous, linear, what are all those things? Linear, homogeneous, first order, because it's a derivative of the first order. Linear, because the thing, my variable, is only to the first power. Homogeneous, because there's no junk over here on the other side. And technically speaking, this is not junk, right? This is basically, this is v to the 1 power, and this is v to the 0 power, v of t to the 0 power equals 0, and it has a constant multiple by that. So, first order means it's the highest order, not just that this is 1, but it's the highest order of all the variable quantities is 1. So g to the 0, anything to the 0 is 1. So technically this quantity shouldn't be on the other side. So once you have all the derivatives set up like that, if there's anything over here, then it means it's a non-homogeneous equation. So you can go back and review all those definitions, but this is that. And the easiest way to solve a linear, homogeneous, I forget all this stuff. What is it? Whatever I said. First order differential equation is a technique. Well, actually, can someone tell me? What technique would I use to figure out what v of t looks like when I have a differential equation that meets all those criteria? Anybody remember? It's basically the first method of solving a differential equation that you used, if you had that yet. Oh, how many people have done differential equations? No. How many people have done calculus 3? Because you could get a little bit there. Is anyone beyond cap? So what is the highest mathematics you're in right now? Abdul, what math are you doing? Calculus 2? Okay, dear, calculus 2, okay. I kind of feeling like I have an intuition for that. I'm not trying to lose you. So forget, I'm sorry, I forgot I was talking, I thinking it was calculus. All right, you know what? Forget all that language that I just used. Let me show you. All right, so you wouldn't know what I'm talking about. Don't worry about it. Still, there's an easy way to figure out the thing. Figure out what v of t is. It's something called separation of variables. It's a technique for solving a differential equation. But I want you to know that this is actually what you're doing. When we used the algebra to build it up, we came at it from a different perspective, a different mathematical perspective. But from the perspective of Newton's second law, the idea is this. This is the genius of the laws of motion, why they're called laws of motion, is that if you can analyze all the forces on a system and understand the functional form of those forces, in this case, the functional form is very easy. It's just a constant times the mass of the object. But other forces like this guy is not. It's a bit more complex because it's associated with the velocity. But if you can figure out the functional form of the forces on an object and then apply the laws of motion, ultimately using mathematics, that gives you a way to specifically determine the functional form of its kinematic quantities, namely its velocity with respect to time. And once you have the velocity with respect to time, you can find the position with respect to time. And that allows you to be able to predict what that object will do within that system as time progresses. So given the functional forms, you know where it's going to be and when it's going to be at that position at a later point in time. And so the idea of using Newton's second law along with the mathematics to solve the what we call differential equations that ultimately Newton's laws, second law, will lead to, that is huge. Like it helps you to be able to characterize a system. Right? So all of that is incorporated in just the idea that you can do that. It's not that Newton actually figured out how to do it. It's also that he understood that that's a thing, right? And again, let me just put that in context. Calculus or none of that was invented, right? Not only was the force, the laws of motion not there, but calculus wasn't even there. So the fact that he could actually conceive of this idea and then do it and then prove that it worked, I mean, it's incredible. It's crazy. It's like crazy. You know, like probably the single greatest accomplishment of humankind. I mean, maybe there's a couple more that's on that same level, like, you know, but that's, yeah, I don't even know how you do something like that. Anyway, that's what we're doing, okay? And this is one of the simplest problems that you can actually have to do it. We have a constant force, simple differential equation, and the method of choice is something called separation of variables. So that's what we're going to do, separation of variables. And in this equation 6, what are the variables? What are the things that are varying as this object falls? Someone tell me. There are two variables. Which one are they? And you actually have a hint of one that I've been talking about the whole time I've been discussing equations 1 through 6. But is that Swan? Yeah. Okay, so David's given one, yeah, David. Velocity is one variable. And anyone, Swan or David Edwards, anyone. What's the next variable? What's the other variable? Time. Wonderful. Thank you, Swan. Those are the two variables. Time, and you can see it here. You can see it in the derivative. This is really dv of t in the numerator and dt in the denominator. So that's telling you the d is, remember, that's, I know you think it's derivative, but it really stands for delta, right? It's delta, basically, it's because remember what the definition of a derivative is, right? It's you know, it's really delta v. It's like the limit as delta t goes to 0 of delta v over delta t. And that's just defined as a dv of t dt. So these little d's here, remember, they really represent delta, the delta quantities, whenever that delta is infinitesimally small. Right? So that's just a change in velocity over a change in time. So that's telling you what's the variables, they're changing, right? So I have two variables. So separation of variables means that I want to get all the, you know, one variable on one side and the other variable change on the other side. And any quantity that is inherently associated with the different variable, put it on the side of that variable. Once I do that, I have essentially two integrals on either side that I can solve, and then that gives me the equation of motion. That's what separation of variables is, okay? So we're going to get all the dvt stuff on one side and all the t stuff on the other side, right? And then we will solve. Now, by convention, the constants, they're constants, so they're not really associated with one variable or another. But there are certain conventional ways like that we like to have the outcome of the formula. So with the constants, we put them on one side or the other based on convention and how we like to see the end result, the form of the end result. So that said, when I solve this, I am going to anticipate a particular result. So I'm going to, first of all, take the g over on the other side. So applying separation of variables, I'm going to yeah. Take the G over. And I know I'm kind of going backwards. I already had it like that in the beginning, but I just, wanted to illustrate what a differential equation is, and you'll get to that. And once you get to it, it won't be the first time you've seen it. Yeah, so you're going to have what, d v of t over dt equals minus g. Now I'm going to take the dt over, and so we'll have d v of t equals minus g dt. So now this is the variables are separated. I have all the stuff with changing velocity on one side and all the stuff with changing time on the other side. And of course, this also clearly shows what we're considering. The way I wrote it shows what we're considering the independent versus the dependent variable, right? The independent variable is time. And we're saying that we're going to find an equation that shows us how the velocity varies with respect to time, which is why we have the v of t in there. That v is not a constant, it's changing. All right? Now, what do we do now? Well, now we integrate. We just integrate, right? Here we integrate, and g is outside of the integration because it's a constant, and we integrate from t equals 0 or t. Technically, I guess t equals 0 or t naught is the time at t equals 0. You can represent that several ways, t naught to t. And this goes from v naught, initial velocity at time t equals 0, to a final velocity. Now here, as a physicist, I'm gonna hand wave or fudge some notation, right? I'm gonna say that this is actually a specific number, right? Because I'm going from a final, velocity at a particular time to velocity at some final time. I guess I could put v of t. I'm gonna use a notation v sub t, which really is v of t again. In fact, actually, I'm gonna use, because that implies something else. I'm gonna do, that implies a terminal speed, which we'll do in a second. I'm just gonna say v of t. That's kind of hand waving notation, right? And I'll show you why in a minute. It's kind of like, for a particular time, that's going to be a number, but I'm doing it as an indefinite integral. So I'm trying to get something that could be any later time, not a specific time. So it's kind of hand waving. I don't know how mathematicians do this, but this is what we do in physics. We kind of just, it's a little bit of a fudging on the symbol, but just understand, definitely it's not fudging in terms of what we're doing. Now, let's integrate. Let's integrate both sides. Actually, I guess it's an indefinite. Since I put in numbers, I made a definite integral, didn't I? But I need to have the limits because I have to give it in the form of the equation that we're gonna compare it to our equations of motion. Now, what is, let's do the right side first, because that's something that you know. Anybody, what is, so Michael Velasquez. When I integrate the right side, what do I get? Michael, are you there? No. So Dennis Escobar, when I integrate the right side of this equation, what do I get? So remember, everybody, protocol. If I call on you, if you're there, immediately take off turn your microphone on so I know you're thinking and I can see you. Otherwise, you maybe walked away. So David, no, okay. Who have another comment? Jesus Avila, you're usually in class. Are you there?
Yes.
Wonderful. Yeah. All right, integrate the right side. Tell me what the right. What's the integral of dt?
T.
T, yes, wonderful. So what I get is minus g, which is there. Who said that? Was that Jesus?
Me.
No, that was not me.
Okay. Yeah, it's not a trick question. Integral of dt is just t, and the limits are from t naught to t. Yeah? Jesus, yes? Good job, Abdul.
Correct.
Jesus?
Yeah.
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 All right. If you need to brush up on that, which you might, go back. So that's, how do they do that? Integral of f, what is it? F of n d dn, no, f of x, I'm trying to do it in the math, f of x, and let's say that f of x is equal to 1. So I guess it's not, yeah, whatever. So no, like you just like, if you looked up in the back, your integral of dx is just x, right? That's how they write. I forget how they write the thing, whatever. Like, it's just that, that's all. That's what this is, okay? I don't know, I can't remember how they write it in math, whatever. That's all it is. And when you put in the limits, say again?
They sometimes use 1, so it's like integral of 1 times dt to make it clear sometimes.
Integral of 1? Yeah, okay, fair enough. Maybe that 3, yeah, integral of 1 dx, and they would just say x or something. I don't know, x to the x. I don't know.
Yeah, that's it.
Yeah. Yeah, okay, whatever, you get it. All right, so, and also, so then D there, what about the right side? What's the right side going to be? Say again? I didn't hear you. Did you? Anybody then?
V.
V of t. Oh, your mic went off. Okay, yeah. V of t.
V of t, yeah, sorry.
Yeah. So over here, you're going to have V of t, V naught to V of t. So that's where I'm kind of fudging a little bit, because I'm saying that it's V of t, but I'm also saying that the limit is V of t. So remember, I'm just kind of, this is really would be a number, not a variable. But I'm trying to say that it's the, I could say final velocity, maybe that's better, right? But I'm saying my final velocity could be at any arbitrary time. That's why I'm writing it at. So I'll leave it at that for now, okay? And then I'll transform it in a minute. So yeah, so now I put in the limits, and what do I get? I get the final velocity minus the initial velocity equals minus, minus g times quantity, the final time minus the initial time. But, you know, my initial time is usually, I set that to be equal to 0. So T naught usually is defined as 0. So that goes out to 0. And when I solve all that for the final, look what I get. I get that the V final, take my initial velocity on the other side, equals V initial minus G times T. And if I then, since I haven't specified a specific time, if I then realize that this V final could be any arbitrary time, then I just leave it as V of t, basically. So then I get V of t is equal to V naught minus G times t. And how about that? Look at that. That's my equation of motion that we got for free fall motion. And in general, when this acceleration is arbitrary, then, you know, it's just V of t equals V naught plus A times t. It's just that in this case, we had the race already. We had defined A as minus G. So that's really how you get, you know, how you, it's the more intermediate way or the advanced way, I guess, if you will, of how you use Newton's laws of motion to figure out the acceleration of a system. Okay? So it's that method that we're going to use in order to derive what the how this equation of motion changes whenever we're considering drag. Because remember, this was not drag. This is basically what we did before, but assuming there was no atmosphere. And with no atmosphere, there's obviously not going to be a drag, right? A drag force. Okay, does everyone understand that process? I just, you know, technically speaking, this was fair game on the first day, right? But, you know, like that's why I say I don't really lean on the calculus in the beginning because, you know, some people are taking calculus concurrently, so they wouldn't have even gotten the integrals yet, you know, a month and a half ago. And it's not necessary. And also there's a whole bunch of other physics we can get out of just looking at it from the algebra perspective. Right? But this is where we're there now, right? You're second, you know, if you are doing calculus concurrently, you definitely should be getting into integration now. And if you're in calculus 2, then, well, you've had everything. You have had all of this, but maybe not applied it in the way that I'm doing it here. Yeah, okay? Everybody good?
Yes.
All right, good. Thank you. Now, let's come back and talk about the physics a little bit before we move on and continue with this. Let's think about what actually happens when something is falling. Oh. So tell me, there is something that happens. Let's think about a guy that is, you know, or woman who is a skydiver, and they, you know, they're doing some sort of show. And let's say that they are in a helicopter and they go way up in the sky. Let's say they go up a mile, maybe three, I guess, maybe 2 miles. I guess you can have a helicopter that high. Yeah, of course you can. Or a small plane, whatever. Maybe a mile and a half. There's 5,280 feet in a mile. So that'll give you kind of a vision. Let's put it to you this way. When you say that the big commercial jets that fly, they fly at about 30,000, 35,000 feet. So that's, and you can see those, right? You can see them where they have the contrails and everything. 30,000 feet is about 5 miles. 36,000 feet is about 6 miles, right? So something that's about 2 miles up is, relatively speaking, that's not that high. You know, in fact, if you saw something 2 miles up in the air, you might not think it's 2 miles up. Even small planes like, you know, single engine planes, Cessnas and things, they can fly 2 miles easy, you know, in the sky. So that's not that high. So a helicopter probably could, even these, you know, helicopters around here, like these copters and stuff, you could probably go up 2 miles and wouldn't need any oxygen or anything like that, you know. It's not that high, relatively speaking. So, you know, you take somebody up 2 miles and they step out of the plane, right? They step out. In fact, I would probably say that that's probably about how high the Army vehicles are, like the C-130s. When you see the commercials of people jumping out of the plane, they're probably about that high. That's probably what 2 miles looks like. Maybe a little higher, but not much more. Right? They're definitely not like 6 miles up, you know, like something like that, okay? So C-130, you know, the big plane, people jump out, that's about 2 miles. Any movie that you saw people jumping out of, that's probably about 2 miles up. Okay. So let's say that they don't even jump out, they just step out. Right? So you step out and you start to fall. Okay. But if there's a drag force on these objects, and let's assume this. Let's assume that we're doing, now I told you that the skydivers go as speed squared, but let's make an assumption just to get an easier problem. Let's make the assumption that the skydiver is doing, his speed is proportional to v, not v squared, but v. What happens, what is the motion, as the object falls, what is happening to the motion? Now, we know that there's acceleration going on, but I'm going to give you a hint. There's something actually happening to the acceleration if we have a drag force that is not a constant force, but is changing as the object speeds up. How is that affecting the motion? Think about it and see if you can give me a response. How is, and more specifically, how is that affecting the acceleration as compared to free fall motion, where the only force on the object is a force of gravity? So think about it, and then I want someone to raise their hand to give a shot at answering the question.
Can you repeat the question, Dr. Brian, please?
Yeah. For free fall motion, the acceleration is constant. It's just g, right? Was that Abdul talking? Who was that talking?
Yeah, that's for me.
Yeah. So for free fall motion, the acceleration is a constant, g. But for drag, for something that's experiencing drag, and let's say it's kv, so it's slow moving, just as a first approximation. If we look at this object, the object now has, well, let's think about it like this. Let's say that I drop an object in free fall, or the guy, the person that steps out. The instant they step out, it's like me dropping an object. What is the speed of the object at that point, Abdul? What is the initial speed?
0.
0. So if the initial speed is 0 and the drag force that I'm considering is equal to a constant times the speed, what is the drag force on the object? I'll make it D. What is the drag force on the object at that instant? Say it.
0.
0, that's right. Now the weight is not 0, the weight is still mg. So at that instant, the acceleration is equal to negative g. But in the next instant, let's say the next second, in the next second, its velocity is non-zero, right?
Yeah.
So if its velocity is non-zero, does this have a drag force on it?
Yeah.
If the drag force is, yeah, because the drag force is proportional to v. So if v is going from 0, then like here, the v initial is 0. Here it has some v. That's the v of t we're talking about over here. Some non-zero velocity. So if that's the case, we see a drag force begin to appear. So at this force, the drag force is relatively small because the speed of the object is small. So maybe we draw it like that. And, it still has its weight. The weight is, the weight is not going to change its magnitude. Whatever it is, it's going to stay that way. Right? But here, drag force is still mg. I'm sorry, the weight is mg, and the drag force is now, so the drag force is actually changing now too, because it's really, I could write it as a d of t equals k v of t, right?
Yeah.
Now, what about the next instant after that? Like say the second second. In the second second, the weight is still mg. But what's happened to the drag force, Abdul, compared to the first second after it was dropped? What's the drag force look like here?
Increases.
Is increased even more.
Yeah.
Why? Because its speed has increased. So I'll call this drag D1 and this is D2, let's say, which is equal to KV2, you know, in the second instance. Yeah. But and so So now, so that's what's happening to the velocity and the drag force. Now let's look at the net force, just qualitatively. What has happened to the net force here compared to here? Has it increased, decreased, or stayed the same?
Decreases.
It decreases. Why, Abdul?
It's because the object is in motion and the velocity and acceleration is increasing. So as the drag force, that's why the initial force decreases. It's like second law of motion.
It is the second law of motion, but you lost me a little bit there. Let's not talk about acceleration yet. Just talk about forces and net force. You said the net force decreases from
as the drag increases.
This point, yeah, as the drag increases.
Yeah.
Now, what is the net force? The net force is going to be a sum, a vector sum of all forces on the object. Net force is that.
Yeah.
So in this case, if I were to write out an equation that represents the net force, and keep in mind down is negative, what would I write here? Well, let's do this one. What would I write for the net force at position 1? So this is 0, this is position 1, this is position 2. So what does the net force look like here? What did I write? Well, I got two forces on the object, right? What are they? What are the two forces?
K and V.
K is not a force.
Oh,
forces are here. Look here.
Oh,
what are
drag
the two
force
forces?
and drag force and acceleration.
Acceleration is not a force. Mg is a weight. Yeah. So if I write it, and keep in mind that down is negative. So what would I write if I were to write it as a vector equation?
Negative GT.
G is not changing. It's just G. It's not a GT.
Okay.
Right?
Yeah, you're right.
Yeah. So tell me what to write.
Negative T.
You're overthinking it, dude. I got two forces. One is mg is pointing down. One is d of t is pointing up. How do I write that if I'm trying to add them? Keeping in consideration their directions.
T. Negative.
Mg minus d.
Well, down is negative and up is positive. So Daniel, did you say something?
VT.
V is not a force. There's no forces in V. I'm asking just, okay, you guys are just really overthinking this. But you're close, Abdul. You're almost there, but down is negative and up is positive. So what do I write? Just change it around.
Mg plus D.
D minus mg.
D
negative
of T minus mg. That's right. That's all I'm asking. Right?
Yeah, right.
Right. So you said mg minus dt, which technically the magnitude would be right, but the direction is not right. Down is negative, up is positive. So dt is pointing up, it's positive. Mg is down, is negative. Okay, that is the net force for this scenario. That's right. But look at this. What's the net force for position 0? What is the net force here? What would I write? How many forces are on the object at position
one.
0? Yes, it's pointing down.
Yeah.
So that's negative. And what's its magnitude? What is the magnitude of the force in this at position 0? What is the force on the object at position 0?
mg.
Yes. So what would I write?
Mg.
It's pointing down.
Negative mg, sorry. Negative mg.
Negative mg. That's right. So now look at this. When I look at these two magnitudes, the net force here is minus mg. The net force, in fact, let's look at an absolute value of the magnitude. So if I look at an absolute value of the magnitudes, right? Which one is greater? The net force at position 1 or the net force at position 0?
Put it in 0.
Yes, the net force at position 0 is greater. Why, Abdul?
Because the object is
Don't overthink it.
there's
Simple answers.
no drag force acting on it, so there's no dt in there.
Okay, complicated. First of all, dt is not a force. That's a time. So no,
Sorry.
no. And there is a direct force act. We just said it. Here, there's one direct force, external force, that's mg. Here, there's two. You're overthinking it. I gave you a hint. I took the absolute value of this thing. I took the absolute value of that thing. Forget the physics, just mathematically. You said this number is greater. Why is that number greater than that number? Simple answer. I know I'm showing tough love. That's all right. I just want to keep it going because things are simple. They're not as simple as you think, right? I know it feels that way because you got to look at all these symbols. It looks like gobbledygook, but it's just a language that's describing things. When it's simple, it doesn't matter that this might look unfamiliar or complex. It's simple, but we still need mathematical things to describe it. So that's why it starts to look complicated because we're being specific, right? I don't know, someone else. I've been picking on you. You did very well. Good job, Abdul. You did very well. Somebody else. Are you there? Hassan Preet. Is that the way is that your first name, Hassan Preet?
Yeah, I was actually gonna ask a question.
Before you go ahead, yeah.
At f of 0, because you were painting us the picture at f of 0. Where is the person at?
They've just, it's this, so there's three pictures, this one, and this one.
Right.
This is the mass here. They've just stepped out of the helicopter. So that's like if I had a mass and I dropped it. That's at the instant that I drop it.
Okay. Okay.
If the instant that I drop it, they're there, the velocity is 0, and the acceleration is g, just like a free-falling object.
Okay.
Right?
Right.
Okay? But it's not free fall because we're assuming that it's there's a atmosphere there. It's not in a vacuum.
Right.
But can you pronounce your first name for me?
Hassanpreet?
Hassanpreet. So I did it right. Yeah. Okay. So
Yeah,
Hassanpreet.
okay.
Yeah. So you tell me, do you agree with what Abdul said that here the net force is greater in magnitude than it is here?
Force is greater in magnitude. At the top one, it's the absolute. It's absolute, correct? It's absolute of negative mg.
Yes.
Um.
And here's the absolute value of what?
Absolute value of dt minus mg.
Okay, that's right.
Change in f of 1.
Excuse me?
Oh, or like the absolute value of change in f of 1.
Yeah, but let's take the right side. Let's look at the right side of those relationships. Yeah.
Okay.
So Abdul said that this number in magnitude is greater than that number. I agree with him, and I asked him why, and he couldn't quite explain why in a simple way. I want you to do that.
Because because dt is always gonna have a number which is gonna subtract and end up greater than the absolute power of negative mg.
It won't be greater. You just said this was greater, and I agree. It's not greater.
Is it because there's no acceleration, Dr. Brian?
No. Again.
Is it because it's a
Say again, Daniel.
Non-negative.
No drag force.
It's absolute value. So it doesn't. We're not talking about positive or negative. Come on, you guys are really overthinking this. Look at the thing.
Is it
Doesn't take into account the mass, right? The
And
drag.
yeah. What do you mean? Like, yeah, it's drag minus weight. Yeah, so clearly we're taking it, yeah.
No, but the drag force itself doesn't take into account the mass, right?
No, they're separate forces.
Okay.
Drag force is kV, weight is mg.
Is it because the
Anybody?
object is at rest?
No, it's not because of that. I mean, it is, but
So, I'm sorry. Is it because at f of 1 it's going down faster? It's falling
No.
faster? No.
not really, not directly, no.
Okay.
Look, folks.
Is it because there's no drag force?
It is. Because there's no drag force. That's true, but what does that mean mathematically? Like, I'm looking for kind of a mathematical answer.
That mean is that d of t equals 0?
Here?
Yeah.
Yeah. So what does that mean about the magnitude of this number compared to the magnitude of that number? I mean, maybe you are saying it, but you're not saying it in a very specific way. All of you, every answer that everyone's given is actually correct, but it's not, you know, yeah.
Sorry, because there's no drag force, the magnitude's going to be greater because there's nothing dragging it along.
Yeah, that's, I mean, you're answering it from a physical point of view. I was just, when I put the absolute value there, I was really just, you know, break it down even simpler than that.
We're not deducting the time. We're not deducting the time from the mass. Is that what it was?
Time is not force. No. Time is, you can't subtract apples from oranges. Time is not a quantity that I can subtract from a force and get something reasonable. So it is indirectly related because of the, but look, let me just answer the question. This number has a magnitude mg, right? This number, I'm subtracting something from that number. So clearly it's not going to be a bigger number. That's all. That's all I'm asking. Right? Right?
Yeah, right.
This is the difference. This is an absolute value. So it's the difference of, but it's the absolute value of the difference of two numbers. So there's no way mathematically that result can be bigger than that result. Right?
Yeah, right.
Right. Now, indirectly, maybe you all were saying that because you were saying all this other stuff, which indirectly relates to it, but it doesn't directly relate to it. And I'm trying to be direct. Like, that's the simplest answer. This is the difference of two numbers. This is a number, but this difference has that number in it. So clearly, that overall result has to be less than this overall result. Yes?
Yes.
Now, I think, Abdul, you came the closest to answering the question in your first answer, but you started off like justifying it backwards. You said that because the acceleration is less or change or something you said, then that means this number is less. But it's the other way around from a physical point of view. The net force dictates the acceleration. That's what Newton's law says. Which comes first, the chicken or the egg? Well, we can't really answer that question. I don't know, but we can definitely answer it in terms of Newton's laws. Which comes first, a net force, a net non-zero force, or an acceleration? Abdul, you answer that. Which one comes first?
Net force.
Yes. A net non-zero force comes before an acceleration. If you do not have a net non-zero force, you've got the first law, no change in velocity, no acceleration. As soon as this guy steps out of the helicopter, there is a net non-zero force on him. It's equal to mg. If he or she were in a vacuum, that force will stay constant and he would fall at a constant acceleration. G would not change. But in this case, she's not in a vacuum. She's in a place where the drag force is proportional to the speed, linearly proportional, and the proportionality constant is K. So in the next instant, there is a non-zero drag force that is acting opposite the direction of motion. So now the overall net force changes. If the overall net force changes, now what happens to the acceleration? Is the acceleration here greater or less than the acceleration in point 0?
Greater.
The acceleration is greater.
Yeah.
You just told me this number was smaller than that number. What does Newton's second law say that this number is equal to?
Math equal.
What does Newton's second law, which is right here, I just wrote it, say that number, which is the net force, is equal to?
0.
No, that's the first law. This is the second law. You're saying the acceleration is 0?
No, mass times acceleration.
Yes. So is this acceleration at this point greater or less or equal to the acceleration at the point right before it?
Oh, it's less.
It's less. Why? Because the net force is less. That's what you just said.
Yeah.
Does everybody see that? Does anyone not see that? Michael Blasquez, do you see that? I understand. Hassan Preet, do you see that? Hassan Preet, are you there?
Yeah, I'm having a little issue with my Zoom right now, so I'm seeing what the issue is.
Okay, all right, cool. Joshua, are you there? Everybody, Muhammad, Dennis Escobar, are you all there? You understand?
Yes, sir.
Yes, sir.
Daniel, okay, good. Yeah, so as this thing falls, this is what we can summarize. As this thing falls, the drag force increases and the acceleration decreases. Because the net force is decreasing as this drag force increases. And the net force is equal to the mass of the object times the acceleration. Clearly the mass of the object is a constant, so it's not changing. So if this net force is decreasing, that must mean the only thing that's decreasing is the acceleration. And it is. So the only time in a real situation where there's an atmosphere where the acceleration of the object is g is the instant that it starts to fall, or the instant that it's there when its velocity is 0. As it falls, the drag force increases and the acceleration decreases. So here, this acceleration is some, let's call it A1, which is less than g, some magnitude less than g. And it's negative because it's going down. We're just dealing with the magnitude. Everybody see that?
Yes.
Okay, cool. Now, let's go to instant 2, this situation. Now, it's increased even more, and the drag force has increased even more. Now, what about the net force at that point, the magnitude? Still, the equation looks the same, but it's dt1. So dt, d of t2 minus mg. What can we say about the absolute value of the net force at position 2 compared to position 1? Greater, smaller, or the same?
Smaller.
Smaller. So yeah, we can write an. Everybody agree?
Professor, could you repeat that again?
Yeah. So I'm just doing the same thing at position 2 as I did at position 1. So this is position 2. This is 2. This is 1, and this is position 0. 0 is not the initial position. So at position 2, I've fallen. Basically, you could call it the second. This is second 1. This is second 2. In the second, is the drag force larger or smaller in position 1? Who just asked me that question?
That was me.
Okay, so Austin Pre. Is the drag force at position 2 greater, equal to, or less than the drag force at position 1?
It'd be greater, no?
It's greater, yes, it's greater. And how do we know that? Well, because we know that the velocity is increasing. We know that just by observing. The velocity is increasing, and if the velocity, let's say speed. The speed is increasing because we just can look at it and we can take data and we can see that. The speed increases, and we know that the drag force is proportional to the speed, then clearly the drag force must be larger at position 2 than it was at position 1. It's that simple, right? Okay. We also know that by Newton's second law that the net force on the object has got to be the vector sum of all the forces on the object. Again, gravity is down, it's constant, it's not changing, the weight that is, excuse me. And the drag force up is opposite direction. So that's why I've written the equation like this. Now I've written it because I know that, you know, I mean, I've just written it in terms of the way that I define the acceleration due to gravity. We define it as negative as down. So I'm specifically using that kind of notation, right? But basically, at this point, the magnitude of the weight is larger than the magnitude of the drag force. Drag force is increasing, but I know that the magnitude of mg is at the very least greater, because if the drag force were greater, then the object would start to go up. So either one of two possibilities: either the weight is greater than the drag force, which clearly it was in the first, initially as it starts to fall, or at the very least, those forces are equal and opposite if the object is moving down. But for now, we haven't, the drag force is increasing. And let's assume that it's still less than mg as it accelerates down. But I can clearly say that the net force at position 2 is less than the net force at position 1. Everybody got that? So that's what I was saying, Hudson Freed. That's how I know. Does that answer your question?
Yes, thank you.
Okay. Now let's compare all the accelerations at position 2, 1, and 0. The acceleration at position 2, is that greater than, equal to, or less than the acceleration at position 1? Anybody?
Great.
All right. Daniel. Or Dami. Is that Dami? Okay.
Oh, actually, it's the same.
You think it's the same? Do you?
Yes. Yes.
So you just told, did you agree that the net force is less in position 2 than here?
Yes.
So you agree that the net force here is less than the net force here?
Yes.
What is Newton's second law, mathematically?
Force is equal to mass times acceleration.
No, net force is equal to mass times acceleration. Say it again.
Net force is equal to mass times acceleration.
Okay, you just told me that the net force here is less than the net force there, right?
Yeah.
So then how can the acceleration here be greater or even equal to the acceleration here? How? What is Newton's second law?
Net force is equal to mass times acceleration.
Okay, has the mass changed from position 2 compared to position 1?
No.
No. But if the net force is equal to the mass times the acceleration, and you just told me that the net force is less, then what does that say about the right side of that equation? And specifically, what does that say about the acceleration, especially if the mass hasn't changed?
The acceleration is less.
The acceleration has to be less. That's right. That's right. the acceleration at position 2 has to be less than the acceleration at position 1. Does everybody see that?
Yes.
You see it now? You see it now, Dami? Do you agree? Dami, do you agree?
Yeah.
Okay, good. So A2 is less than A1 is less than G. We can keep doing that, right? In the next second, same thing. So what can we say about the acceleration of the object as the object falls?
It decreases.
It's decreasing. Yes. Wonderful. So in reality, something does not fall at a constant acceleration. That's an ideal case. Even this thing is not falling at a constant acceleration. The acceleration is decreasing as it falls. Yes.
Professor, I have a question.
Yeah.
So if the acceleration is increasing, if the velocity is increasing, why does the acceleration decrease?
Excellent question. Excellent question. Which tells me that we still quite haven't distinguished the difference between acceleration and velocity. They are different quantities. They are not the same quantity. And it's a little bit deceiving because usually they trend in the same way. If you're in your car and you press the accelerator actually changes. It actually, acceleration is increasing. You know, it's usually not even constant, but the acceleration increases and the velocity increases. But even if you press the accelerator, you know, and held the accelerator such that you maintain the constant acceleration, still, you know, the acceleration is, in some instance, it had to go from 0 to some non-value, so that kind of implies an increase, even though after a certain time you could hold it constant. But the velocity is increasing, right? So we don't really distinguish, at least qualitatively a lot of times, between acceleration and velocity. But this is a situation where it's showing that they really are different and they can be doing very different things on the same object simultaneously. And the answer to your question is simple. The reason is because they're two different physical quantities. They're related to one another, but one does not directly, actually it's true, one does directly. This is the way it goes. The net force determines the acceleration and is directly associated with that, but the acceleration is directly associated with velocity. So in this case, the velocity continues to increase, but what's happening, it continues to change, but what's happening to the change in velocity as time goes on? Let me put it to you this way. Yeah, like the change in velocity is the rate at which the velocity is changing. That's technically the acceleration. You just said that, so let's back up, And I'm gonna go with you, Dami. We've just deduced that what's happening to the acceleration as the object falls, Dami?
It's decreasing.
It's decreasing, that's right. So if the acceleration is decreasing, now let's talk about the velocity, but we can talk about the velocity in two ways. We can talk about the magnitude of velocity, but then we can also talk about, so yeah. How do I say this? So I guess three different ways. We could talk about, so acceleration, you said the velocity is decreasing. Sorry, you said the acceleration is decreasing. But if I were to relate the acceleration to the velocity in qualitative terms, I could say that the acceleration is the rate at which the velocity is changing. Agreed? Dami, agreed?
Yes.
Yes. So you say that the acceleration is, what did you say? You said it's changing, you said it's decreasing, right? You got that far, right?
Yeah. It says decreasing.
Yeah, so the acceleration is decreasing. So in terms of the language that I was just using, I could say that the rate at which the velocity is changing is decreasing. Agreed?
Yes.
Yes. Okay. So if the rate at which the velocity is changing is decreasing, what is the minimum value at which that rate and change of velocity would achieve? In other words, what is the limit on the acceleration? Like, how low will it go?
0.
0. 0. 0. That's right. And when will the rate of change of the acceleration, sorry, the rate of change of the velocity be 0? Compared, like in terms of the magnitudes of the forces. When will that happen?
I'm sorry, one more time, Professor?
Let me ask a different question. When the rate of change, when the acceleration, so basically what you told me is that the acceleration at some point is going to be 0, right?
Yes.
I agree. When the acceleration is 0, what happens to the velocity?
0.
No. Because if that's the case, that means that the object would just, some point it would just stop and hover in the middle of space.
Constant.
Constant. So it reaches a value, and then from that point on, it stays at that value. That actually is such a popular quantity that we actually give it a name. In fact, movies have been made from that. What is that? What do we call that?
Vector?
What do we, excuse me? Abdul, what did you say?
Vector quantity?
No. No. It is a vector quantity, but it's a vector quantity that has a specific name.
Quantum? Is
No.
it quantum? No.
No, that's not what I'm looking for.
Wait, a movie name, right?
Yeah. The velocity is no longer changing, and it falls at a constant velocity from that point on. What is that called? What type of velocity is that?
Terminal velocity?
Terminal velocity. Yes. Terminal velocity or terminals. Did you have to look up the movie?
I did.
Yeah, I mean, years ago, I forgot who was in the movie. I forget. I think it was, I don't know. I remember it was back in the 80s, I think. Terminal velocity. Yeah. Terminal speed. You've heard of that. Everybody knows that. Terminal speed. Right? You've heard that before. Well, this is where it comes from. Here, the speed, the initial speed is 0, and it falls. As it's falling, the drag force increases. The acceleration is decreasing. So it's not the rate of change of velocity is decreasing. Whenever that rate of change of velocity hits 0, then the velocity is not changing anymore. And from that point on, it falls at a constant speed. Unless now we know that we've made skydiving into an art form. So the objects have those flying things on; they fly around. Well, that's definitely not. You never reach a constant terminal speed in that case. But again, remember, we're assuming a point particle, something that can't do all that. So it's an inanimate object. Once it jumps out, and we're assuming that the skydiver is like that, right? It's a special case. But it's falling, and it can't fly around or anything like that. It's just completely dependent upon two forces, weight and drag. Because when you're flying, you introduce all other kinds of forces, lift, and it's no real thrusting case, but there's lift there, and lift is not the same thing as drag. It's a different type of force. And you can fly, you can change the direction of the forces when the wings are, those web things in between. All that is changing all those different. So that's how it can do all that kind of stuff. So that's more complex motion. That's not what we're talking about. Only two forces: drag force, which is depending on the, the magnitude of the speed, is always direction of the opposite motion. The motion is always straight down. So very simple kind of motion there. In that case, it's going to reach a terminal speed. Terminal speed. And from that point on, it falls with that terminal speed. And the acceleration of the object from that point on is what? Once the object reaches terminal speed, what is the acceleration of the object? Asymptotic. Zero. Zero. So what can you say then? So which law applies? The first, from terminal speed on, which law applies? The first law or the second law? The first law. Yeah, the first law. So what we're doing is we're really looking at the object in a special case. We're looking at the object when it falls from 0 to its terminal speed. And we even have a name for it. The terminal speed is V of t. That's why I didn't want to use V of t over there. V of t is terminal speed. Yeah, was that Dami? You had a question?
Yeah. When the object reaches terminal velocity, is the drag force equal to the weight?
Yes, it must be. That's good. Very good. That was the next question I was going to ask. What is? I actually asked it earlier, but I don't think I lit it up to you appropriately. What is the relationship of the drag force to the weight when the object reaches terminal speed? Well, they're equal, which means that the drag force has a maximum. The acceleration has a minimum, 0, and the drag force has a maximum value. It can't just increase indefinitely. It increases to a maximum value, and that maximum value is the magnitude of the weight. So when the drag force is equal and opposite to the weight, it's at that point that the acceleration is 0 and that the speed of the object is at its terminal speed.
Professor, quick
Yes.
question. As acceleration is decreasing, would that make V of t negative?
Yeah, I mean, it is negative, but just because we define it that way.
Okay.
There's another, you don't have to even look at the dynamics to know that it's not that V of t is negative. I mean, when you say, did you say V of t or V sub t?
V of t.
Yeah, V of t. V of t is negative just because the object is going down, and we define down as negative.
Okay.
Yeah. So here, let's be careful to talk about V in terms of a magnitude and in terms of a vector.
Right. Okay.
But yeah, like that's why. Yeah, if you did this, so when you look at absolute value, you're just getting magnitude. I wanted to focus on the magnitude, and I didn't want to talk about the signs. But we can now talk about signs. Yeah, if you actually looked at this as a vector quantity, it's negative, and it's going to give you a negative acceleration. But we made that work out. We did that. We imposed that on the problem because we're defining down as negative. That's why I keep saying that.
Okay.
Right? When you define down any vector that's pointing down is negative, whether it's a force or an acceleration or a velocity, we did that by defining down as negative. That's what this is doing. So as long as mg is greater than dt, yeah, that net force is going to be negative, which means the acceleration is going to be negative, which means that the problem that we're really working out is this problem. Right? It's always going to make this quantity negative because we're defining the acceleration as negative. In other words, in this situation, even though it's not g, I know we say ay is negative g, but in this case, ay is just inherently negative because it's going down. And that will all work out because we set it up that way.
Right.
Got it?
Yeah.
Yeah, yeah. But at terminal speed, it's the acceleration is 0, right? And yeah, Vy is still going negative because it's going down. That's why. So I guess you could think of this as 4 steps. This is the way I normally teach it. I mean, it's an infinite number of steps, but if because you can break up dt in whatever increment you want. But if you kind of think of it in seconds, which is kind of a nice increment because that's MKS, you know, and I don't know that this thing will get to terminal velocity in 4 seconds. You know, I'm just, and it doesn't have to be seconds. Maybe it's like 7. I don't know what it is, but I'm just looking at equal increments of time. That's all. At some point, this thing is going to reach a terminal speed. And that's going to be the point when dt reaches a maximum, and the maximum value has to be mg. How do I know that the maximum, how do I know that dt won't be larger, reach a magnitude larger than mg? How do I know that? Anybody? Why must that be the physical upper limit on the drag force?
Because the object will be going in the opposite direction if the drag force is greater.
Yes, good job. Yeah, this is what you would see. I would drop this object right now. It would drop and the speed would increase to the terminal speed. And then if the drag force got larger than the weight, it would start to decelerate. So the velocity would start to decrease. So the velocity is 0, it would increase to a maximum value. At that maximum value, well, I get it, yeah, maximum value, the drag force would be equal and opposite to the weight. But then the drag force would continue to increase, and then it will start to decelerate. So the velocity will start to go down again. At some point, the velocity would be 0 again, and then the object will start to go up. Now, there might be some universes where that happens, where the drag force is like that, or I don't know. I mean, anything is possible, right? If you start, you know, jumping to quantum mechanics and considering parallel universes, there's no physical reason why some universe where that's not the, I mean, it could be, who knows? Maybe there's a universe where the atmosphere is made of stuff that is spongy. I don't know, like, you know, maybe the molecules act in such a way, you know, it could be. It could be. We don't know. But in this universe, in this atmosphere, this is the relationship. So at some point, and so in, you know, in this solar system, you know, in our Earth, that would look illogical because that's not what happens. So because something doing that spontaneously and going up like that doesn't seem reasonable in our world because that's not the way our stuff interacts, right? So what does seem reasonable, what is reasonable, is that the object reaches a terminal speed. And then from that point on, the object continues to move down at a constant speed. And everywhere along the way, that drag force is equal in magnitude and opposite to the weight until it hits the ground. Unless, of course, we put, you know, a fly suit, you know, make it more complex system where the thing can fly around for whatever reason, which we're not doing that. Okay? Got it?
Yes.
Okay. Okay. All right. We got what? 10 minutes, 12 minutes before the break. Okay. All right. Well, let's solve this problem because we're going to need that. We can use this to figure out what the terminal speed is. We can use this scenario. The scenario where the object is falling under the first law, terminal speed. Well, and then we can use that for the more complex scenario. So when we hit terminal speed, as someone told me earlier, a few minutes ago, it's the first law that applies to the situation, not the second law. The first law applies. Net force equals 0. And that's the situation, as I just wrote here, where the weight down equals the terminal speed up. And I'll do it for slow moving. The acceleration is 0. So the acceleration is going from g, magnitude of g, to 0. And the velocity, or the speed, has gone from a magnitude of 0 to the terminal speed. V of t is now v sub t. So v sub t is a constant number, that's the terminal speed. V of t is the variable. So yeah, so in that range of motion, you know, that happens to a certain period, and then at that point, the thing continues to fall down at a constant speed. So if we apply the first law to that scenario,
Professor?
then what we, yes.
I'm sorry. So just to clarify, V of t is the variable, and V sub t is that a constant?
Yeah, it's a constant.
Okay.
It's terminal speed. V sub t means terminal speed. It's a constant.
Okay.
So, you know, and maybe I should put in here, V of, I don't know what time that happens, but V of t, whatever time it is, you know, t terminal, I don't know, like, you know, it's going to change for different problems, but whatever time it takes the object to fall from velocity is 0 to its terminal speed, that's a specific time at which it's like the end of that range. You know, like if you look at the overall motion, right? Say, I guess I have it here, but if you kind of came back, right, and looked at the, how did I represent that here? Yeah, I don't know. Yeah, I guess I didn't, whatever. You know, like, say this is the ground. Let's do it over here. This is the ground. And, you know, this is the helicopter. We jumped out of the helicopter, right? So if I could break up the motion into various parts, during this part, the velocity is changing, v of t. And during this part, I fall with a constant velocity, a constant speed, you know, constant velocity, terminal speed. Well, it's only in this range where the velocity is changing. But that has two extremes. One where one is where v of t is 0, you know, v naught, and the other where v of t has reached its maximum value, which is equal to the terminal speed. That's all I'm saying. And then from that point on, the speed is not variable, it's just v sub t. Get it? What I'm saying?
Yeah, I understand. Thank you.
Yeah. So the equation of motion then that we're going to derive only applies within this part of the motion. From that point on, the velocity is a constant. So maybe that's throwing you off a little bit. Let's just say that the velocity is v sub t, excuse me, terminal speed. So it's in that. So in this regime, the second law applies. In this regime, the first law applies. So we're going to apply the first law, and yes, v sub t is a constant, but we can use that to figure out what that constant is in terms of basically the quantities of the object. All right, let's do it.
Professor?
Yes.
Sorry to take you back.
Sorry.
When the object reaches terminal velocity and the drag force is equal to the weight, what keeps the object in motion? Like what makes it keep going down?
That's a very good question, dude. That's a very good question. Very good question. Yes. Let's see if someone can answer it. It's a quantity that we haven't defined yet, but it is something that you have an intuition for. And it's kind of inherent in the first law, actually. It is. You can answer it by, even though we don't know that quantity. So the direct answer, there's an indirect answer that is basically in the first law. And I've just kind of given you the hint because I've told you that the first law applies in this part of the problem here. So Donna, you tell me, what is the first law?
Law of inertia.
Yeah, but tell me, say it, and apply it qualitatively to that part of the problem.
An object at rest or in motion or in yeah, in an object at rest or in motion will continue to remain at a constant velocity if it's not acted on by net external force that causes it to
Good.
change.
So let's just take that right there. Once I enter in this regime, I'm moving in a straight line, you know, moving at constant speed in a straight line, right?
Yeah.
Right? And what is the net force everywhere inside of that regime where I'm moving?
Zero.
Zero. So I'm already moving, regardless of how I got moving. When I enter this regime, regime, I have a constant speed in a straight line, and I'm just going to continue doing that unless a net force comes along and a net non-zero force acts on me. And as long as d of t equals, or d, I guess now d, the drag force equals mg, the net force is going to stay zero, and I'll continue along with that motion. That's one way to answer the question, given the dynamic and kinematic concepts that we've already defined. But it's kind of a long way around. What we ultimately will define is something called linear momentum. We'll do that next chapter. Well, chapter, whatever it's chapter. In chapters 6 or 7 and 8. We'll define momentum. I guess I've already done it to a certain degree because I defined it when we did the second law. Technically, but we haven't talked about it. But the short answer to that question is that the reason it continues moving is because it has linear momentum. And if that linear momentum doesn't change, then it's going to continue with whatever motion it has. And remember, we did associate momentum with the Newton's second law as well. We said that Newton's second law is equal to, the net force is equal to mass times the acceleration, or another way to state it is that the net force is equal to the time rate of change of linear momentum. And what we'll show is that the linear momentum is constant when the net force is zero for the first law. And so therefore, there's no reason for the linear momentum to change unless there's a net external force. And if it doesn't, then it continues with whatever momentum it has. So that's a different way to answer the same question. Got it?
Yep.
Okay. Very good question. Very good question. So, any other questions before I proceed? All right, so we're all convinced. We're at a place where we're in the situation where the net force is zero, we're falling at a constant speed, terminal speed. We know that the first law applies, and we're going to apply the first law in order to figure out what that terminal speed is. Capiche? Everybody got it? All right, let's do it, because it's only going to take two or three steps. It's easy. Apply the first law. Net force equals zero. What forces are on the object? They're constant forces now, both of them. The drag force is not constant anymore. It's d, and we're going to assume slow moving. Okay, I know it's not really slow, but just as an approximation. So it's the same equation. This guy, d, which is now a constant, so I won't write d of t, I'll just write ds minus mg equals zero. So d of s equals mg. But now I can use the concept of drag force. We said that for slow moving, it's equal to a constant, the drag coefficient for that, for air equals, I think a good, reasonable magnitude, I think in a book is like 25 kilograms per second. I mean, actually that would be fast moving, so it would be 25 kilograms per meter. But whatever, this is not really reasonable for this. So we'd have to, I don't know what the number would be because it's not really slow moving. That's not really the equation that applies. But anyway, at any rate, this is more for like a pearl falling in syrup or something like that. But the K would be much larger then. It would have to be much larger. So probably like more like 3,000 would be the thing. But that's not a realistic drag coefficient for air, obviously, because air doesn't have the thickness of syrup, So anyway, K is equal to V, so KV is equal to mg, right? And that V is V sub t. So the terminal speed then would be equal to mg divided by K. There you go. Yeah. So that would be the terminal speed. Now, you can see that it's constant because for the particular environment, you know, the atmosphere, the K thing is not going for the fluid, I guess you would say. The K is not going to, and I'm using fluid kind of generally. You've probably heard of like air called a fluid before, you know, or maybe you haven't, but you can kind of use that in a general sense, technically. But that's a constant. It doesn't change. M is a constant, G is a constant. So it shows you terminal speed is constant as it falls down. Now, we're going to use that to be able to define the equation of motion up here. So let's go back and get use that V of t to figure out what the equation of motion is in the regime where the velocity is changing. But I guess it's break time now. Yes, it is, exactly. So let me just set it up so I want you to maybe work on this a little bit, see if you can do it. We're going to come back and we have to solve that differential equation. We're going to do it the same way we did this. But now we've got two forces. We've got the drag force and we've got the weight in that regime right here where the thing is changing. Now, I'm going to erase this for now because I think I could probably do it almost in one section of the board so we can apply it to what I did over here and see what the differences are as I go through, okay? So it's the second law in here. And since it's the second law, the net force equals mass times acceleration, okay? But now we got to be careful because this acceleration is no longer constant. We just said it's changing. And this net force is going to be d of t minus mg equals ma of t. Now let's put in the definition of acceleration and let's put in the drag force. The drag force is k v of t minus mg, that's still a constant, but now this thing is m d v of t dt. Look at that. That is the differential equation that we have to solve essentially. I'm going to put it in the form of a differential like I did wherever it was. I don't know. Where did I do that? I think I've erased it. I don't know. But I guess it was down here. Yeah. And then just to show you that it's still a linear homogeneous blah, 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 which means that we can use separation of variables to do it. So I take everything over. I have 0 equals. Yeah, so first of all, let me just mess around with it a little bit. I'm going to, well, I'll get it, yeah. So I'm going to take the k v of t and the minus mg and take it over to the other side. So I have 0 equals m d v of t dt. And then that'll be a minus k v of t and then a plus mg. I'm going to divide everything through by m because I want to get it in a form where I only have the coefficient of the dv of the ddt term is 1. So multiplying through by m, I'm going to have dv of t dt minus k v of t over m plus g. I think that's what I want. Nope, sorry. That's not what I want to do. Scratch that. That's not the route I want to go. But at least you can see from here that yeah, that's not the route I want to go. From here, you can see that it's still a linear, because any term that any of the velocity terms, they're only raised to the first power. That's what that means. The velocity itself, right? So linear. It's not like velocity squared or velocity cubed or anything like that. That's what linear is. It's referring to the power of the variable. And same thing with time. It's not time squared or whatever. First order refers to the order of the derivative. And again, the derivative is just the first derivative of the velocity. So that's the order. So linear, first order. Homogeneous means that whenever I have the powers of the variable of the independent variable on one side, and again, this is going to be v of t to the 0 power, I don't have anything on the other side, like a log of the velocity or other stuff like that, anything like that. That's non-homogeneous would be that. So it's a linear first order homogeneous differential equation, which means I can apply separation of variables, the easiest technique to use. So that's my justification. Now, I'm going to go one step further, then I'll let you go break to set it up for you. Again, it was kind of trivial here, the fact that I took the G over and did it that way. But what the next couple of steps I'm about to do is the same thing. I'm kind of manipulating this because I want the form of the outcome to be a certain way that so I can compare it. A conventional way we do that. So I'm going to go back to, what's the easiest way to get there? I always kind of confuse me a little bit. The easiest way is to kind of go back to this step and then manipulate it from there. For me anyway, I don't know. 3, 4. So I'm just going to go back to 3. Or that 5. So I have, just to get back there. I just want to do this just to show you, to make a comparison. It's a justification as to why we can do separation of variables. So going back to this step, so K, V of T. I guess I don't have to, but I don't want to do too many things at once and get lost or confuse it. Okay, so I'm back here. So I'm going to So what I have to do is I have to get all the dt stuff on one side and all the t stuff on one side. But more than that, here I do actually have some junk that has v of t in it. Like this is a v of t, right? So I have to get it. I have to get it so that, yeah. In fact, let me do this. Let me do this. This is an easy way to see it. I'm going to divide through by k, not by, did I say that? Yeah, I divided by n by 4, but no, that's not what I want to do. I want to divide everything by k. If I divide everything by k, so that by k and that by k, because you know what I do on one side, I have to do the other side. Basically, it's the same as multiplying through by 1 over k. The k here cancels. Yeah. So this is what I have. I have v of t minus mg divided by k equals m divided by k, and I have dv of t over dt. So that's a better way to see it. I got to separate variables now. And I need to have everything on one side that has t stuff and everything on the other side that has velocity stuff. Look at this. Clearly that's a velocity, so that belongs on the side of the differential that has velocity, clearly. But look at this. That's mg over k. What is that? Anybody? What is that? What is that quantity? Mg over k. Give you a hint, we just solved for it. Somebody tell me. Is everybody there?
Terminal velocity.
Yeah, that's the terminal speed. We just solved for it here. So I can substitute that in. So clearly that should also be on the side with dv as well. And if you worked out this term right here, m over k, you would realize that that has units of 1 over seconds. You could work that out. Okay. So so let's get all stuff. So basically you cross multiply. I guess you could take this stuff and put it in the denominator, you know, of that side, and the m over k 1 over dt comes to the other side. So you like basically it's like a cross multiplication. So so on the left side, I'm going to take this over, the 1 over dt and the m over k. So over here, I'll have k over m times dt equals dv of t over v sub t minus mg over k. Yeah. And I can see somewhere along the way I lost a minus sign. Where is it? I lost a minus sign. Somewhere along the way I lost a minus sign. Oh, yeah. It's actually here. I kind of screwed up a little bit. No, I didn't screw up. I just, I went against convention because I was teaching a certain way. This quantity here is inherently net. You know how we said that, yeah, I should have put it in. I should have put it in. You know how we said that, yeah, I forgot to do that because I was so focused on other stuff. Sorry. I'm gonna have to go back and do it up here. You know how we said that whenever we write equations of motion, we want to write the acceleration so that it's inherently positive? That's what we've been doing the whole time, right? Like whenever we did dynamics and equation, you know, the Newton's second law, we make it so that we're subtracting the largest force from the smallest force. right? That's how we always set it up whenever we were, you know, the objects on a plane and stuff like that, right? But here I started off talking about free fall motion because it's going in a negative direction. That's the equation. But that's from the point of view of kinematics. That essentially this equation, this acceleration is inherently negative. But if I want to make it inherently positive, all I have to do is, you know, acknowledge that, but then put in a minus sign. Basically, the this net force is an inherently negative quantity, which basically we were saying all along. But I allowed that to be the case just to describe that, you know, the mathematics, because I wanted to make it, you know, like I said here, you can put a negative sign there. But generally speaking, we don't write acceleration as inherently negative. We write it as explicitly negative, meaning that if it's positive, we don't have to write a sign. But if it's negative, we have to say that. So I'm going to go back and do that for all of this, which all I have to do is to put a negative sign right there. Because I know that this net force is negative. Why? Because minus mg has a larger magnitude than dt, as long as it's in that regime where the drag force is not yet equal to mg. So to fix that, I have to go back and put in, and I'm going to make it a different. Now, because now I'm looking at it from the point of view of dynamics, and I want to write it conventionally in the way that we've been doing. So if there's a negative sign there, then a negative times a negative makes that a positive acceleration. That's what I'm saying. Negative, negative. Yeah, let's just skip that step. Like, so this is the same equation here. So I just had that step in there to, maybe I don't even need the number. I don't know, whatever, I already done it, but whatever. That was just to show you that, to justify why I can do what I'm doing in separation of variables. So here, there's going to be a negative out here. Put that in. And then negative here. And that's the same negative sign here. I need that in there so that I can, it's just because I need, it's not that I could do it the way I'm doing it, but I'm going to get a different form of the answer as to what I know you're going to have in your book. Because conventionally, we always set up differential equations, at least in physics, so that the acceleration is positive. So I'm just making it work out what I know will be the answer that we will conventionally like. So here, I can flip this, I can multiply through the negative sign now. So I'm going to have k over m dt is equal to dv of t. And this is going to be basically, I'm going to substitute in for the terminal speed, which is v sub t, excuse me. So it's going to be a positive v sub t minus v of t. Okay, there you go. And that's the differential equation that I now need to solve, which I can solve very easily. So let's go to break now, and we can make it a working break. That this is a differential equation you have to solve. If everything is separated, I've got all the velocity stuff on one side, I've got all the time stuff on the other side, and you know, I just realized something. Holy crap, I didn't know that. I don't think I ever saw that before. This thing has, well, I know that it has units of inverse of time, but so that has units of 1 over seconds. But that time, that is the time that it takes for it to go to terminal speed. Actually, I guess I did see, but it's yeah. We'll see it in a second. I'll see it in I think that is. But we'll see it once we get the equation in motion. We can look at it differently. Anyway, or it's the inverse of that time. But anyway, you can solve this. On one side, we integrate and we get time on the other side, we're going to get a, equation for velocity. So you can work on that during the break and see if you can get the equation. And I'm sure they give the answer in your book. So, but they don't do the steps. And I don't think they did the steps, intermediate steps. But yeah. So why don't we take, what time is it? 3:49. Why don't we go to break now? And so 3:49, I say it's 3:50. So let's come back. Let's take 15 minutes. 15. So actually, let's take a 20-minute break so you can work on it and work on it too now, at least for 5 or 10 minutes. Don't just not work on it at all and take a 20-minute break. Because I want you to give you a break, but I want you to give you a little time to work on it. So and I don't want you to have to work during your break. So see if you can solve that. And why don't you do a couple things too? See, solve that. If you do that, go back and get the x for this. So again, it's positive. Let's assume positive in general, positive AFT. Well, actually, it's this one. So this is the one we had for velocity. But the next step is to get the position. So the next step is to substitute in dx dt for the definition of velocity equals v naught minus gt. Go ahead and work that out. Separate the variables and then get the equation of motion for time. And get the velocity equation for this. And if you're so daring, go ahead and do it again to get the position equation for a drag. Okay? So that's 3 problems. Do this first. Then go over here, and that should be simple for you to get the equation of motion for position versus time and for free fall, because you have the answer. You know what the answer should be. Then come back to the equation that you had for v of t, put in the definition of position of velocity, that dx dt equals v, put that in the result you get for this, and see if you can go to one step further and get the position equation for the drag equation. Both of those, velocity versus time and position. Actually, it's not going to be in their book, is it? Because they would have used fast moving, and we're using slow moving. But still, do it for slow moving, and we can compare the answers. Make sure you get the right answer for a slow moving equation of motion for velocity and for position, in the case of a slow moving drag force. So does everyone understand what I'm asking you to do? 3 things. Get v of t for a slow drag, x of t for slow drag, and go ahead and get the x of t for free fall motion, which you know what the answer should be already. All right? Abdul, do you know what to do? Abdul, you there?
Dr. Brian. Dr. Brian.
Yeah. All right. All right, cool. So let's take maybe 20, 25 minutes, give you a chance to work on it. A working break, and a 10-minute, 15-minute break, and then come back and start working on it. All right? Okay. If I can knock this out for you before we leave. Yeah. So, here. So this just integrates to t, right? Oh man, I should have kept it out. Yeah, my bad. I might have messed you up a little bit. I didn't have to go back. I could have kept that minus sign over here. Let me do that. Yeah, right. Because I did this a different way in my notes. Sorry, I need to have that minus sign out over here. Sorry about that. We could keep it like this. Yeah, I could, yeah. Sorry. Actually, I did have to go back and put in the minus sign, but I could have just kept it right over here. I need it over there. So I'm going to bring that minus sign back over there. So maybe that threw you off, probably. And so this is going to be, and this is just to get it in a certain format. So if the minus sign is over here, I have minus Km dt equals, actually, let me just put it up here. Just do it, so it saves space. So just bring the minus sign over here. So this is actually the differential equation I need to solve. Solve all that. All right. So I'm going to integrate, just like before, and go from 0 to t over here. And then over here, I integrate and go from v naught to v final over here. So this integrates to minus Km times t. And over here, this is just a log, right? This is a constant. I could put in the v of t here, and we're going to do it here. V sub t, sorry. And this is 1 over t, so it's, you know, you get the log of, you know, x plus b or something like that. You know, it's just log, or 1 over x. Integral of 1 over x is log. Integral of 1 over x, you know, plus or minus b is log of x plus or minus b. So in this case, this is going to give you ln of quantity of v of t minus v of t minus v sub t, and that is from 0 to v final, assuming that v naught is v final, which it is in this case. And so what we will get is minus k over m times t is equal to, putting in the limits, I get log of ln of v final minus v sub t. In fact, I'm going to go ahead and write the v final as a v of t, because that's, you know, it's at any arbitrary time. I know, don't let that confuse you, right? I know I got a v of t in there and then substitute in, but whatever. Or maybe I'll do it at the end so you know what I mean. So minus v sub t, and then minus log of v sub t. Oh, and there's a minus sign in there, but I'm taking the absolute value of it, right? Because it's the minus is there, so that's log of minus v sub t. But then I can take the absolute value. Yeah. So next step, I take the absolute value of that. So and then so minus k m t equals log of v final minus v t minus log v sub t. Now there's an identity that log of a minus log of b is equal to log of a divided by b. Remember that? So I'm going to use that over here so I can write this differently. So minus k m t is equal to log v f minus v sub t over v sub t. Okay. Then I'm going to take that. Remember, there's also the property that the exponential of log of x equals x. So I take the log of both sides. The log of this thing is just e to the minus km times t. The log of the other thing is, I'm sorry, the exponential of this thing is of the right side is e to the minus km over t. Exponential of the other side is just, it just gets the argument out. So exponential of the log of all that stuff, in the end, it just gives me e to the minus k over m times t equals vf minus v sub t over v sub t. Everybody see that? Okay. Okay. Multiply through by the v sub t. And I'm going to have so v sub t e to the minus km times t equals, now this v final, now I'm gonna, let's do this. Let's do a couple things. The v final, it could be at any arbitrary time, so it's really just v of t. I didn't want to throw that in and confuse you, but it's just v of t, right? Like for in general. And this thing, let's define a time constant. The I can define a time constant, tau. I told you what tc equals. It's actually not. I was making a mistake. It's not the time it takes to get to the constant velocity. It's a percentage of that time. So we define tc as m over k, and we'll see what that time is in a minute. Yeah. So we define that tau c, the time constant. So I'm going to put that in, plug both of those into equation 14. So call that 15a and 15b. So if I plug that in, then I'm going to have e to the minus t over tau c. And that equals v of t, formerly v final, minus v sub t. Oh, I'd already multiplied through, so the v, I forgot to multiply. So the v sub t in the denominator is over here as well. That's already there. That's the multiplies the exponent. So I took this over, substituted in time constant here. You remember this is m over k and this is k over m, so that's why I have that in the denominator. And then vf is v of t. So now I'm going to take the v sub t as a constant. I take it over on the other side. So that gives me the equation of motion for velocity, that the velocity at any time as it falls is equal to v sub t, the terminal speed, minus, e plus v sub t, e to the minus t over tau c. And you can see that this equation is reasonable because I'm multiplying this number v sub t times a number that this is basically 1 over e. And as t goes to infinity, that whole number goes to 0. So technically speaking, it's saying that you don't really get to the terminal speed unless you get to, until you get to t equals infinity. But what you'll see is that, you know, for 3 seconds might be that, you know, a certain amount of time, it might only take you get to 3 seconds or any time. It depends on what this time constant is. It depends on the viscosity of the fluid, how large that K number is. But basically, it might take you 5 seconds to get to a place where you're 98% of the terminal speed. So in one time constant, you're 98% of the terminal speed. In three time constants, whatever the change is practically negligible. And it might even be a millisecond or whatever. It just depends on what it is. But I can clean this up a little bit. I can get to a better form. Factor out the V sub t. So I have V of t is equal to V sub t times this quantity e to the 1 minus e, so e to the 1 plus e minus t over tau c. And that's usually the form that you see the, the result. Like that. And if you graph it, it's something that we normally do, graph that function, it gives you a visual representation of the terminal speed. It's going to look something like this. So I'm reaching a maximum value of the speed. That maximum value is V sub t. And it does that exponentially. So you start off at a velocity 0. So this is, you know, V of t, right, and along the y-axis. This is t along the x-axis. So what you get is a curve that looks like this. So it approaches the terminal speed exponentially. Now, if you put in one time constant and work that out, so what is the value of, that's a problem that's normally done, right? What is the value of the terminal speed at t equals one time constant tau c? This is a nice form to have it in because you put tau c in, that equals, you know, basically that equals on here, V sub t times 1 minus e to the minus 1. And that gives you a very specific value, right? When I put tau c in here, I have tau c over tau c, which is minus 1. Turns out that that's a specific value. That number equals 0.63 0.63 V sub t. So that's telling you that you're at 63% of the terminal speed in one time constant. So the way we represent that on our graph is this value here. It's going to be about someplace like that. So in one time constant t tau c, I'm at 0.63 V sub t. So it took me one time constant to get to 63% of my terminal speed, whatever that time constant is. So it's reasonable to think that in 2 or 3 time constants, I'm going to be approaching the terminal speed. And that time constant could be 2 seconds. So in, you know, 10, you know, by 15 seconds, even though technically speaking, according to this problem, you don't really reach terminal speed until you get to t equals infinity. After 15 seconds or so, the difference in the change of the velocity as it approaches the tangential speed is going to be way over here someplace. So it's so small that it's practically negligible. So you can say that the time constant is about 15 seconds. That's the way these things are done. Yeah. So that's that. That's equation of motion for drag. And as I mentioned, in order to get the position equation, you now do separation of variables again. You take this and put dx dt into that equation. So for x of t, you place dx of t dt is equal to v of t plus v of t e to the minus t over tau c. Do separation of variables again, and then solve for that equation of motion, which is actually not very difficult. It's very easy to get that equation of motion. So, you know, those look very different from, I mean, this is comparable to what I just erased, that velocity, you know, for in a vacuum, v of t equals v naught plus a times t when you're not taking drag, but you just put drag in, and the velocity with respect to time goes from a linear equation to an exponential equation, exponential function. So, you know, yeah. All right, before you leave class, let me just, let's bring it down. That's a lot. This was a lot, probably one of the most intense classes we've had all semester. So give me some feedback. How do you feel about this? Dami, you were pretty participatory today. What do you think about this stuff? Dami, are you there? Didier, what about you?
I understood it, Professor.
Say again?
I got it.
Good. Abdul, you're also prepared. What about you? How do you feel about this? Abdul, you there? Okay.
Yeah, right.
Oh yeah. What do you think?
No, other than using like forces, so there is symbol. That's the only thing. But overall, it's not that bad. Yeah.
What did you say? You cut out a little bit. You cut out. I didn't hear the first part. What'd you say?
I'm saying like overall, it's easy. It's just like in math, you know how with calculus we use numbers and physics we're using forces, like symbols and stuff. So that's the only part. But overall, it's it's fine.
Cool. Thank you, David Nwabo. Daniel Nwabo. Yeah, everybody. Yeah. So you know, Dennis Escobar, David. Yes. So just, you know, you should see, they should have this in your book. I'm pretty sure. Let me get my child in resume, see what degree they covered it. Now, yours is, you know where to find the book, the digital book. I don't know to what degree they did all the explanation. Let's see. Conservation of energy, work, forces, motion. Centripetal. So yeah, this chapter ends with centripetal motion. Where's drag? Drag force, terminal speed. Oh, they go a little bit more in depth. Here, they do give you talk about, oh, that's fast moving. Okay. So they give you what the terminal speed looks like. Okay. So the older text I used to use, it did both. This one just focuses, it looks like it just focuses on v squared. And it gives you what that constant is in turn, it breaks down the constant a bit more. But I don't see the equation of motion. It doesn't really derive it for you. It doesn't really give you, I've given you a lot more than, but this is an older version of the book. I'm curious to see what they have in the newer version. Because most calculus-based books actually go a little bit more in depth than that. Let's see here. I'm gonna put my screen on screen share to see. Okay. So let's go to Ali. Actually, we can go down here. Forces of motion. 6, yeah. Friction, sliding block, parachuters. Huh. Here, maybe? No. Here? No. I don't know. That's not well, in the, it's interesting. Now here, they don't even, parachute. I don't know what that is. Those are probably examples. Just go to the book itself. The textbook. Drag. Okay. Drag internal speed. Drag force internal speed. Yeah, okay, so drag force, terminal speed, blah, blah, blah. They don't have much at all. Doesn't really explain everything I kind of went through. So they just give you the formula, have you solve for the terminal speed. Okay, fair enough. They don't give an equation of motion. So in my equation, this is for fast moving, and the beta that I have is equal to 1/2 C rho A. So they're breaking. I told you you could break it down and show you what it actually is. All the equation. So talk a little bit about what I was talking about there. Yeah, they don't actually. Oh, here you go. So they give you the equation. That's in free fall when it's at this is the equation for terminal speed. And they show you where you get that from. But then I don't see them going back anywhere and actually deriving the equation of motion. Yeah. Well, yeah. Most calculus-based books, they will actually. The other one we used to use, the Universe Citizens of Mastery, they actually go through and do what I did here and show you a bit more. But so I gave you a little bit more detail, and you can match that up with what they have there, because it's doable. It's doable. I think it's worth doing it. And they don't even give you the graph. I think it's really important to do that, because you're going to see this again. You're going to see all this kind of mathematics when we look at circuits. This stuff comes up again twice in the next semester for AC circuits and things like that. So I think it's worthwhile to get accustomed to the mathematics right now. But go ahead. I mean, I would go ahead and do what I asked you to do. The other two, get the equation of motion for X for both free fall and you can go back and do this again for the fast moving. It's not going to be much more complex mathematically, just because it's V squared. It's not really. I don't believe so. I think I've done it once or twice. So yeah. I'll let you go with that. Yeah, that's it. So, yeah, as I said, I'm working on trying to figure out this, maybe I didn't now, so I think I did, but this course, the homework and stuff, I'm trying to figure out how to, maybe overthinking it, but I need to contact the representative. So I'll keep working. But in the meantime, I've given you some class stuff to do. When your notes, you can work through that, and that'll help you to continue to understand the specific notes that we've discussed. Any questions or problems, struggles, gripes? Well, I'll let you go. Remember to vote. Yes.
Professor, when is today's meeting going to be posted?
So it takes about a few hours for it to post.
Okay.
But you can go there. I think I sent you that note. Now, what I normally do is take a link and put it on the modules. I haven't done that all semester for this class, but you can still, you go to the Zoom, then in there, there'll be several tabs. One of them will say iCloud recordings or something like that.
Yeah.
Or there is, yeah, or there's one that says all meetings, previous meetings, either one that you can have access. When you click on that, then it'll show all the saved meetings by date. And you click on it, it takes you to another page, and then you'll have an audio recording, a video recording, and also a transcript on all those pages.
Right. Okay. Thank you.
When will we start creating the canvas? Yeah, like I've been talking about, that's what I'm saying. I've been talking about that the whole semester, the whole class. I don't know how to specifically assign it, but you can, in the meantime, you can go through and look at what I showed you earlier, this class. Start working on the practice sessions and the sessions in the back of the book. I have to contact the representative to figure out how to put the homeworks in so that they're graded. And it's not quite the same as it was prior to integration. So I couldn't quite figure that out yet, but I will, okay? All right. Okay? Anything else?
Thank you, Professor.
All right, thank you. Y'all be well, be safe.
Thank you, Professor.
All right, thank you.
Dr. Gamble,
Yes.
I have a question.
Mm-hmm.
I got kind of lost, like in the steps.
Where?
I think mostly when you brought in the LN.
Okay, yeah, let's go back to that. Let me show you what that is. So that was between this step and this step, between 7 and 8, right?
Correct.
Okay, what I'm doing there is this. Let's come over here. I'm just using a basic integral that you, what math are you in right now?
Well, I finished all my calculus.
Okay, so you just don't remember this. Now you have to go back and kind of brush up on this and make it practical. So
Yeah.
the integral of, what is the integral of 1 over x? dx?
It's LN, right?
Well, yeah, either log x or ln. Yeah, it's ln x, right? Absolute value. What is the integral of 1 over x plus a?
Would it be ln of x plus a?
Yeah, ln of x plus a. That's what this is. But I have a minus sign there. So like, put a minus sign here, and there's a minus sign here. That's all this is. It looks more complicated than it is. That's all this is. But it's dv, right? My x is v of t, so dx is dv of t. That's all.
So it's
That's this step to that step.
1 is equal ln of d.
V of t is a constant. Let me do it over here for you. So what I have is, it's the integral of dv, and I'll take the like the independent variable thing makes it look more complicated. So it's dv over v minus, and v of t is a number, it's a constant. So the variable is v. So it's the same thing. These are the same integrals. You see that? Where x of t is, or not, it's not even of t. I mean, it's, yeah, I guess x is like t, and v is like x, and v of t is like the constant a. I just use different symbols. Do you see that?
Okay, I see. Yeah, I see it now. I got confused because I think I saw like a T next to the DV. On number 7.
It is. It is. It's because I'm putting in the
Yeah.
time dependence. I could have done that here. This is like, they don't
Oh, that's
actually
right.
usually write this. Yeah, they
Yeah.
don't write that in mathematics, but it's like y and x, right? So it's like, I don't know, like it would be like, I use x, just maybe that was a bad thing to use because they use it, but it would be like, what if I had dy of y minus x, right? Then now this is ln of y minus a, right? But I could make this explicitly the explicit dependence of x, right? It's actually the integral of dy of x, right? Because it's over y of x minus, and this should be some constant, sorry, a, sorry about that. You know what I mean? Like, right,
Yeah.
y of x equals x, whatever, some function of x. That's all that is. It doesn't have to be there. It's just like I'm just writing it in terms of the
Oh.
independent variable. But dv of t and dv, it means the same thing. In the same way
Okay, I
that,
see it now. Yeah.
Yeah. So like in math, right, you can write y, or you can write y of x. Still, it means the same thing. It can mean the same thing.
Okay.
That
Yeah. I get that part now.
okay? Cool.
After your number 10, you changed it to ln of a minus ln of b.
No. I was showing you that this is an identity I'm using. This is an identity in math.
Okay, I see it. Yeah.
The log of a number minus the log of another number is equal to the log of the first number divided by the second number.
Okay, I see it.
So I use that to convert all of this to this.
Okay. And then you brought in the e to get rid of the ln, correct?
It's not a bringing in the e. I operated. I took the log of both sides.
Okay.
So I took the exponential of both sides. So the exponential of this is just going to be e to that, raised to that. The exponential of a log gets the argument out. So I didn't actually show that. Well, I did it here, but I didn't write all the stuff in there. I'm taking the exponential of a logarithm, so it brings out the argument.
Correct. Yes.
Yeah.
Damn, I forgot those steps.
Yeah, you got it. Yeah. So that's why I'm putting them all in, because this kind of derivation, there's 2 things we do next semester where we do the exact same thing. A lot of people don't actually present it here, but I like to, because it is kind of, it actually is easy. It's not easy in the sense that a lot of this stuff, but if you do it once or twice, then it all comes back, And what's nice about it is that it's not just a math problem. We're actually applying it to something that we think about, that we experience every day. Anything that drops, like even when I drop this thing, it's not really dropping at a constant speed. It's actually doing this. Now, the point in which it increases, it goes to its terminal speed might be very small because the drag force might be small, but it's got a drag force on it. Clearly, the drag force is not 0 on this.
Yeah.
So this is a very applicable thing, and it's actually a problem that we can work out and get an answer that is, it's actually pretty correct. If we could take data on something like this and apply it to this, we would get this curve. Like it would, it's pretty accurate.
Yeah.
Yeah. So it's a nice thing to work out, especially considering the fact that we're going to see the same kind of mathematics in certain circuits that we're going to be working with next semester. So it's nice to review it.
And then your VF and is that JC?
Where? What number?
After number 14 on the next row column.
So here 15A and 15B?
Yes, correct. Yeah.
No, I'm just saying that here again, that's the fudging thing that I'm doing, is that when you take an integral, where is it? Here. So technically speaking, when I integrate, I'm going to, you know, you only put numbers in as integration variables, right? Like
Yeah.
these aren't variables, right? But the thing is, I don't really know at what time I'm going to reach. Well, first of all, I'm in that regime that I showed you where I'm going from velocity, the initial velocity, which in this case is 0, to some
Yes.
quote unquote final velocity. But it's a final velocity in that regime where my velocity is increasing up to the terminal speed.
Okay.
Once I'm past that, it's different physics. It's the first law, and it's not even like a differential equation. It's just a constant, right?
Okay.
So this equation, it applies. It could be any final velocity for any particular time in that region where my velocity is increasing from 0 to the terminal speed, right? Right?
Yes, correct.
Okay, so the way that I worked out the integral to emphasize physically what's happening, I did a definite integral where I put in like a specific time t and a specific velocity. But it could be any time within that range. This equation still applies. So I don't really want to write this as VF, which implies a number, right? Because I didn't put in a specific time. Now that I understand that it is a number and it's in any arbitrary number within that regime, I'm just simply, I shouldn't even put an equal sign here. It should be like an arrow. I'm just replacing the V final,
Okay.
yeah, with the V of t. I don't know how to do that
Okay.
mathematically, like the correct way to do that, because I've never seen a mathematician do it. What I used to do was actually put a V of t up here. But that's also all more confusing because, you know, you don't, this is the variable, so how, what does it make sense to have a variable up here? Doesn't make sense.
Yeah.
So what I started doing is just taking a specific example, then saying, you know, if I did that at any time, I want to get the functional form of the velocity. So that's where I kind of do this little hand wave, that's what I call it, hand waving, bringing it back to a variable and putting it in so I can get the functional form of that velocity. That's what that means. But you're right, I should have put equal there. I missed, should have been just an arrow, yeah. All right?
Yeah, now it makes way more sense. Yeah, I just got thrown off with the ln and the BF equal to.
Yeah, of course. I mean, that's natural because you haven't seen that, probably haven't even thought about that in a while. And now I mean, the physics is what I want you to think about. And that stuff, you know, you just probably hadn't done it in a while. But you just go through it once or twice, and I promise you, it'll make perfect sense.
Yeah,
now
I'm
that
gonna go over it.
Yeah. Okay?
Yeah.
Yeah. All right, good.
Just one more thing, Professor. Sorry.
Yes, all right.
So I looked at my my notes, and I see that you replaced dt for k v times t.
What number?
Right below the force is equal to ma times t. The very first one. Number 1 and 2 and 3.
Oh yeah. What now? Here?
So you replace your correct. Yeah, like you replace your dt for k dt.
Yeah. You question about that?
Yeah, can you explain that just a little bit more?
Yeah, that's just what we said. That's just the definition of the drag force. That's all.
Okay.
So when I first started, I said we have two types of drag forces. One is for slow moving, and it's equal to a constant times is proportional to speed. For fast moving, it's equal to a constant. I think I use a different constant, beta times the square of the speed. These are definitions.
Okay.
That's what the drag force equals. You know, like weight is defined as mg, right?
Okay.
3 equal signs. Drag force for a slow moving object, like a rock in oil, is a constant associated with the oil times the speed. But for a fast moving object, it's defined. This is empirical. People just looked at a bunch of things and then they wrote down these equations and said that's, you know, when you see like a skydiver falling out of a plane and do data, when you kind of extrapolate the data, it gives you that the force is equal to a constant associated with a bunch of stuff times the square of the speed.
Okay.
So it's just defined that way. Now over here, I again fudged again because I wanted to do K, I wanted to do the work out the problem with the slow moving first.
Yeah,
So
okay.
I made the assumption that even though it's not really true, that a skydiver jumping out of a plane, maybe I should just do it differently. It's like, maybe I shouldn't even do that. Maybe I should say something like, if I dropped a pearl into an oil, then these would be the forces on it. It would have the weight going down and the drag force would be up, basically.
Okay.
So dt is equal to kb of t for something like that system. So that's where that comes from. It's just the definition of what the drag force is for something that is in, for a slow moving system. Got it?
Yes.
Yeah.
Why did you put the dv over dt on the right side on number 3 for the m times dv times t over?
That's the definition of oh, why did I do it? Where's that? Oh, that's this. Oh,
Yeah.
here, you mean?
Yeah, that
That's
part.
just that's the definition of acceleration. Acceleration is defined as the limit as delta t goes to 0 of v final minus v initial divided by t final minus t initial. And what is that? That's the derivative. It's the derivative of the change in velocity, v of t, versus the change in time, dt. It's the definition of a derivative.
Okay.
Acceleration is equal to the time derivative of the velocity. So I substituted that in here.
Okay, I see it. Yep, got it.